Sure, I don't mind going over it. Well, I'm just good. I'll answer. Oh, I'm sorry. I'm not going to take like the whole list. How about I do what Jeremy suggested, and then I'll get a list. Is that better?
Yes.
All right. And good idea, because I don't really. It's been a rough couple days. I might not have a firm understanding of where I left off or what I even covered. So let's talk specifically about the electric field. Answering your question is so disingenuous to say it's easy and can be all boiled down to a single expression, but it's the truth. The electric field is defined in a very rudimentary and I'd only say haphazard kind of way, because it's defined on what it does rather than what it is. So an electric field is defined based on. I do worry that sometimes I will not hear things. So, but I'm less worried that I will hear things that you don't hear. That is a lower worry on my level of worry things. So electric fields are defined by what they do, which is a stupid way to define them. Now, they're defined that way now. In a week, they'll be defined in a much more elegant way by something that's more holistically able to determine where electric fields come from. But we're not there yet. And so I can't use this method for you in the same way that I can't also use this method for determining what an electric field is, which there are just different ways to determine electric fields that we're not prepared to deal with yet. So understand that I'm supposed to introduce electric fields today, well, last week, without actually giving you what it is. So I tried to give you something more tangible by comparing it to the gravitational field. But the truth is, an electric field is defined by what it does. If a particle experiences a force due to its electric properties, meaning due to its charge, then we say that field is an electric field. The size of that electric field is proportional to the force it experiences. To determine the size of the field, we take the force it experiences and divide out by the test charge's value. So if I have a region in space and I place a test particle here in that space, and I say that test particle has a value of not 8, not infinity, it is lowercase q. So get over saying it's an 8. I'm done hearing it. So many of you have said that. It's a q. I mean, how else could I write q?
Just a straight line.
There we go. So from now on, I'll try not to loop my q all the way back. I know you guys have never seen cursive before, but that's all it is. So.
It looks like a Q. It's a beautiful Q.
My ex is
I think it needs to be sharper. There you go.
You know, I'm recording this right now. So I don't want to say anything that might get me in trouble. Gonna get fired this year. That's the goal. So. That's not a dream. Is it your dream? So, since record has been hit, we're still walking down this road. I place a charge somewhere in space. If that charge experiences a force, then we would state that the electric field that caused this force is equivalent to the force divided by the size of the test charge in that space. So, it's rhetorical in its definition. And I understand why that can be difficult, but that also tells you exactly what you would have to do to determine an electric field. You would place a particle someplace in space, giving it some simple test charge value like Q. You would determine the net force on that particle due to all other conditions of the space. Then when done, you would determine the electric field by dividing out by the value of the charge. So let's put that to practice. Let's say I have, instead of this test charge, I say, okay, there are 4 charges of various values in a region of space. All right, just 4 random charges, Q1, Q2, Q3, and Q4. If I want to know the electric field in this region of space, and I'm going to be very careful about how I state this, you guys are trying to look around each other to see what I put on the board. I literally just drew 4 circles, putting pluses and minuses wherever, and just randomly place them. You could do the exact same thing, and it looks totally different than this by just placing 4 round things with a couple pluses and a couple minuses on them, and label them Q1 to Q4. Doesn't matter. This next thing, the thing that you will miss writing down but actually matters, is the issue. So stop looking around the backs of everybody's big heads, and here's what you need to actually write down. That the electric field in this space is probably complicated. There's a lot of charges in this place. When you're asked to calculate the electric field, you are often asked to calculate the electric field for a specific location in space. When you're asked to calculate the electric field, you are almost always asked to calculate the electric field for specific locations in space. You're told it's a distance r away from the line of charge. It's located at the x in the diagram. It's at point P on the line. You'll be given some place in which you're asked to find the electric field. Now, you may be asked to come up with an expression for the electric field in a region of space. That's fine. But understand, your expression probably has to do with parameters about that space. Now, if you don't understand what I just said there, like if that whole thing was too esoteric for you, that over here. You understand why I can't do that over here? I don't know what the electric field looks like here. I know from, what do we think it looks like over here? I mean, near each charge, they each have an electric field, like so. That one has electric field like that. That one has an electric field like this. That one has an electric field like this. Near each charge is pretty easy. Now, the negative one, what direction would a positive particle go? Would it go away from the negative charge or towards it?
Towards it.
But it would still have a certain amount of radial symmetry. The problem isn't these individual charges, and I see your hand, I'm ignoring you. The problem is where the middle ground shows up. I don't know what the electric field begins to look like at places in between these charges, where these electric fields interact. This is what was missing from our conversation. The electric field is trying to give us a sense of what the space looks like around these particles. But there could be times where the electric field from one particle and the electric field from another particle kind of interact and produce a net electric field. For that, we might need to kind of think about what's happening. Now, technically, if I want to find the electric field for this region of space, I could place a point charge everywhere in space and find the individual force on that point charge, begin to develop a pattern of where all the F's would point and the size of all those F's, and then divide all those F's by Q and add them all together, and that creates what my map of this electric field would look like. I don't want to do that, but I could do that. Or I could say, maybe, on a test question, I would not do this either, find the electric field at point P. And I say, okay, that's point P right there. I want to find this electric field at point P. Point P is right here. Well, that will be a complicated question, won't it? Because in each case, I would have to determine the distance to point P from each of these charges. I would have to determine the direction of each of the forces on a test charge that I place at point P. And then I would have to add vectorially each of those forces together so I could get the net force on the particle at point P. And then I would have to divide by the amount of my test charge to get the net electric field at point P. Now, if you didn't write all those things down, I could say those slower because that is exactly what you would have to do. Point for point. Something that you actually could do. We've done this problem before. I haven't given you enough information to physically do it here, but you could. Step one would be to find all of these individual distances. Place a test charge at point P, assigning it test value Q. Find each of the forces from every pair between a charge in space and my test charge. So I'm not going to write them all down because that's kind of a ludicrous experiment, but I think you understand what I would have to do for each one of those. But then, and here's the hard part, I'd have to add them together vectorially, meaning break all of the forces up into x components and y components and add all the x components together first and all the y components together second, and then find the net force on the particle. And even then, I wouldn't be done. If I want the electric field, I still have to divide that by the value of the test charge. Now, that's very laborious. And allow me to make a quick pause here. Correct? Net force equals ma? So if you wanted to iterate what this object would do, I would apply that there's an acceleration acting on my object at this instant. Now, depending on how accurate you wish to be, you create a time scale that is appropriate for what you wish to do. So for example, perhaps I say that for a small change in t, we'll treat this acceleration like it is constant for a small region of space. Maybe small enough to move that particle from here to here. And I don't know if this is the direction that the net force would push it. It's just likely based on where the particles are, it'd probably be somewhere in that direction. Is that okay so far? So now my particle released from rest moved to there. And it's been whatever time slice you've decided. So now my particle has some velocity and is now in a new place in space. Everybody good so far? So you know that R1, R2, R3, and R4 all changed, right? They all changed a little bit. So you'd find out what the new R1, R2, R3, and R4 are by using this distance and trig to find all the new R's. Then you would find the new force. Then you would find the new acceleration, and you would apply that acceleration for your next increment of time. This is iterating a process. Now you understand, once you've put this all into a spreadsheet once, you can have it iterate as many times as you want, right? Constantly recalculate. All you have to do is program your spreadsheet to change R1, R2, and R3 each time by doing some trig. Spreadsheets are good at that. And find out what the new velocity is by doing a Galilean motion equation, right? Because you're assuming the acceleration is constant over this interval. Find the new velocity, the new position, start over again. This is actually how they do it. They write a program. You could do it in Excel yourself, so that way you wouldn't have to write a program. You could just, do some equations inside Excel, and you could do this. A couple of years ago, a student came in for an AP seminar project, and they wanted to do something like this. And it was not easy, but it wasn't hard. There wasn't 4 different charges all in some random location. They were going from here to someplace else, and it was pretty straightforward. But you could do it this way. So you can iterate your path. Famously, this is the process that was used in the movie and book, The Martian, to talk about alternate different ways you could reach Mars and Earth when they were trying to save Watney off the planet. That's what the what's his name? I don't remember the name of the actor, but it was the guy who basically did he was the one in the famous scene with the pen, kept clicking it on people's heads and stuff and walking around the room. But anyways, that's what he did. He sit in a room with a supercomputer and he sent all that into the computer to have it run an iteration map, and it came out with an iteration map, and then he presented his findings to the folks. You program the computer once to do this. Now, we don't do it this way nowadays. Nowadays, we understand a little bit more, and we've been able to stand on the shoulders of other people's calculations. So they have like pre-processed routes between planets based on their known locations over time, and can create routes for different types of fuel usage and stuff like that. But back in the old days, if you want to see an interesting use of this, look up the Voyager trajectories. And there's plenty of videos that show what they did. And those were all worked out almost by hand. And they're kind of interesting. All right, so I spent a lot of time on that. You had 2 questions. You got 1. That's what you're getting. Because we got to move on a bit from this. So if you're asking yourself, Mr. Shelton, what do I need to take away from this? Here's what you need to take away. I have a square with 3 charges on it. And we'll say Q, positive Q, negative 2Q, and positive 2Q, located at the corners of a square. Find the electric field at the other corner. This is a problem I could ask you to do and feel reasonably sure it's within the confines of this class and would utilize the information that we've done so far. It has all the kinds of things in it that are useful for us and that it exploits a certain symmetry. Wouldn't you agree? It's a square. So I know that the forces are going to lie in specific directions that I can use without having to do too much trig. For example, I know that if I place a test charge here of value Q, then between these two, there'll be a force in the x direction this way, and that force would be QQK over S squared. Good so far? And I'm reasonably comfortable that you could probably do that for all of the other forces that are acting on it. And then do the next couple steps. Add together F1, F2, F3, breaking it up into the x direction and the y direction. Summing them together and getting the total force on the particle. I think that's not unreasonable. Good so far? I don't want to do it this way. I think we can skip a couple steps. First, I think we can stop thinking that every time we want to find the electric field, we have to place a test charge there. Have you noticed every time I place a test charge, I just end up dividing it out at the end? It shouldn't be too big a stretch to realize that the electric field from a point charge could be just written like that. Right, that the electric field anywhere around a point charge is going to have that circular symmetry, and therefore I could treat the electric field in the same way I could treat just the force between 2 particles. But just don't put the particle there anymore. Just say, okay, there's my region of space. And now each one of these isn't an F, but is E. And I don't have to put that Q in there. And I would say that each of these now is E1, E2, and E3. And I'll add them together to find the total electric field. Right. If it's point charges, Coulomb's law really gives me an expression for electric fields around point charges. Is that good so far? Is this answering your question, Jeremy?
Yeah.
Pretty thorough? What's that?
Could you do one of the problems from the homework?
I'll be happy to, but I'm going to say one more thing before I do. There's a popular parlance out there, and that's not the right word, but I don't have the right word, so that you could map field lines based on a few simple rules to give you a picture of what the electric field might look like. To understand where I'm going with this, imagine I have just a single point charge in space. I've already just kind of described it, but the field would stream away from this particle, filling the space in all directions. Now, it's not three-dimensional, but by drawing in these 8 arrows, I get a clear indication of what this field must look like. Right? What I want you to understand is I drew the lines starting at the positive charge with arrows extending away. Field lines go from positive charges towards negative charges. There's no negative charge here, so I just drew my field lines as they would extend away from a positive charge. I originated them all at the positive charge, but didn't add any lines after I left the charge. Did you notice that? There's 8 lines, whether I'm close to the charge or far away from the charge. Did you also notice that the lines get further apart? You see that clearly? Because electric field mapping is a real thing. Mapping a field helps you understand the space around charged particles and has with it some information. And these things are important. First, if you're going to map field lines, the closer together the lines are, the more concentrated the electric field. The further apart they are, the weaker the electric field. Should seem obvious, but a particle out here would experience less force than a particle right here. But we can see it now because if the electric field lines are spaced far apart, then they are going to suggest less electric field. So what if I bring in another charge? It's negative. Now, it would have electric field lines. I'm going to draw them in a different color. That would look something like this. Now, I want to be careful here, but you realize that the way I'm drawing this, there's going to be an interaction between the green arrows and the white arrows. Right? There's 2 electric fields, one coming from the negative charge and one coming from the positive charge. And this is the most important thing I'm going to say about this before I move on. In space, though, they combine to produce only one electric field. A particle located here might experience 2 contributions to an electric field, but it can only be pushed in one direction. So, there is a single electric field line at this location. So when there's more than one charge and you're attempting to figure out what the electric field would look like, remember, electric field lines point from where a positive charge starts, they originate at positive charges, and terminate at negative charges and tell you what a positive charge would do. Is it a surprise that if you placed a positive charge out in this space, the positive charge would be pushed away from this charge and towards this charge? And right here at this location, it would be experiencing a force this way from this charge and this way from that charge. Agreed? Making the net force kind of that direction. So it is possible to kind of theorize about what the electric field might look like between a couple of charged particles. Generally, the lines are going to start from the positive and go towards the negative. And we'll still have other field lines around this particle, but the ones in between are going to be affected by the existence of the other particle. How about between two positive charges? A particle directly in the middle would experience no force, right? Pushed equally in both directions. So a particle in the middle would see no electric field. So electric field there's got to be 0. Well, what happens to that line that was leaving this particle in this direction and this particle in this direction? Well, there's another rule. And the rule states this: the lines can't cross. So if two arrows are coming together, they bend away. So that's what you do. I state that these two lines bend away. I don't know the strength of the particles, so and we're just trying to get an estimate for what the space is like to help us understand what the electric field might be doing. So field lines originate at positive particles, terminate at negative particles. They can't cross, and they provide a picture of the total electric field in the region of space. You'll probably never draw field lines like this. It's just a way of visualizing the space around charged particles. So, with all that being said, which one in the homework would you like me to perform?
But what about the electron? Like how much it would take to accelerate?
I don't know which number that is, so I have to read.
I think it's like 6 or something. I think it's 5.
5. What electric field could accelerate an electron at G? You could get an expression for your answer or an actual numerical value. All right. So, electric field equals force divided by charge. Agreed? And net force equals MA. So,
I should have done it at the end of last year.
back to work. Quite literally, I did not expect this question to cause you much difficulty. So here we go. Ready? If it's being accelerated at G, the net force has to equal mg. So if I want to find the electric field that would do that, the electric field would have to equal mg divided by q. Now, we're talking about an electron here. So this would have to be the mass of an electron times g divided by the charge on the electron, which is the elementary charge. That's the answer. That was all you had to do for number 5.
Is the elementary charge written as E?
The office took away some of it, and to Jeremy. E is 1.6 times 10 to the negative 19.
But how do you distinguish between that E and Euler's number?
Context.
That's it?
That's science. You know how many things have the symbol mu or lambda? We run out of letters, dude. Imagine if I have a single point charge in space. I could be asked to figure out what the electric field looks like everywhere in this space, which wouldn't be all that hard to do. There's a certain amount of symmetry, right? You're aware of the symmetry around this point charge, aren't you? That as long as I am a distance r away here, then the electric field at that point is probably the same size as r over there. Can you see far enough into the future to see why that would be true? If you can't, if you just shook your head and three of you did, then imagine what would happen if I placed a charge here, Q, and that same charge over here, Q. In your head, can you say to yourself, well, this one's very likely to experience the same size force here as here? Can you make that distinction? Is that okay? Because if you can go that far and realize, okay, that force has got to be Q, K over R squared in both places, then I'm also therefore saying the electric field must be Q, K over R squared in both places. And I'm going further now. R can be any value, right? From right up against that central charge to something very far away. I have now given us the electric field in all of space around this one charge, because no matter where I am in this region of space, I am a different distance of r away. Good so far? There's spherical symmetry around this point. So the only thing I really need to give is one value for r, and I've covered all the electric fields everywhere around this single point charge. Okay so far? We sure? Because I can't look at this one charge that the electric field probably goes in this direction around the outside of this charge. And I'm using these little arrows to kind of give us an idea that the electric field is going to push a positive particle away from the charge. And that electric field would be radially away from that charge. Right? No matter where I put my test charge, won't it experience a force of repulsion? And I say radial, meaning any radial line connecting one place to the other would be the direction of that force, therefore the direction of that electric field. Is that good so far? Well,